guess.
I remember I had it like on, I think just the email stuff,
Yeah, yeah. I think apart from that, there's also some sort of hash that UVLearns returns. I don't remember if uh, you get an email with that or if that just shows up after you upload it. But yeah,
sorry about that, I won't let that happen.
no, it's all right. Do you guys have ideas for projects yet? Okay. Uh, One of the things that I'm a little bit, I'm trying to figure out is what level of complexity I should set as the floor of what is acceptable for me. Because um, when I was getting my master's, the kind of projects that we had to do were a lot simpler than the kind of stuff that is available today. Um, I took the same class in 2017, and what I had built for my project was a real-time handwritten digit classifier. That's it. I open up my webcam, hold up a piece of paper with something written on it, and it would just spit out what number it was. And things have changed so much since then that that's closer to a hello world now, and that wouldn't fly. Maybe in a like a sophomore year undergrad class, probably that would be acceptable, or junior, but yeah. So yeah, yeah. If this was a deep learning class, then putting the emphasis on training a model from scratch would have been a bit higher. But I, since we're trying to do something vision, um, if you're using something that's pre-trained, that I don't really care, because as long as the problem that you're solving is interesting to you and involves having to think about the image domain and features and what you're trying to extract, why what you're using works. Um, yeah, the goal is to get you to think, but I also don't want it to be the case that you come up to me like the amount of exposure that people in this class have, that there's some variance to that. So I don't want someone for whom all of this is new to have to come up with something very complex. The It's like the equality and equity thing. Uh, I think the amount of effort required should be uniform, and that's a bit hard for me to estimate. I guess what I could do is, based on your proposals and whatever I think of it, if the feedback that I give or any addition that I want you to make to it, if it's too complex, then just push back. Um, that way we can find a happy medium, I guess. Mm, If you change your method, that is fine. If you change what data you're working with, that's also fine. As long as the general, like, broader sort of subdomain of computer vision that you're aiming for, as long as there's something that ties together the evolution of your project, that would be fine. Uh, Not weekly. Um, I think I gave you guys 2 weeks between the proposal and the refined proposal slash first report. I think that should give you enough time to just set up and get started and maybe test out a few existing either post-form deterministic solutions or pre-trained models or whatever, and get a sense of how challenging making changes to that will be. I think 2 weeks should be good for that. I'm assuming most people don't have more than one class for the summer. Do you guys have more than one class? Okay. Do you have other classes? How many? Okay. Yeah. Uh, Machine learning in 6 weeks. Wow. And I thought I had it hard. Where are you at in class? Like, what topics are they talking about? Oh, okay. Jesus.
They kind of stuff about how
Oh, so that's 6 hours a week? Okay, wow, that's a lot. Who's teaching that? So it's also a student instructor? Oh, geez. Woof. 6 hours a week is tough, man. Wait, I mean, like, I think I'm also doing close to the same. Just have it split differently. 2 hours? Wait, that doesn't add up. I'm doing 3 a week. Yeah, okay. Yeah. I don't think I could handle 6 hours a week. Maybe this class, if I had to do it again, reusing these slides and building on them, I could probably do 6 hours a week. But right now, since I'm doing everything from scratch, it takes every free minute I have, more or less. Yeah. Oh, wow.
they started off Fridays.
This lab's cool.
Higher, it's probably
What part of it are you working on? Okay. Hmm. Sounds fun. I think one of the big challenges is just being able to visualize what's going on, especially with machine learning kind of stuff. For me at least, math is intimidating. I really have to sit down and like try to break every equation down until it stops being just Greek. And that's kind of what it was like when I was first taking a machine learning class here during my master's, 2017. I think it's only now that I've finally started wrapping my head around what actually goes on under the hood. It just took a lot of exposure to it and trying to visualize things. With a lot of the other stuff that we're introduced to earlier on, like if you're doing physics or whatever, then the sequence in which topics progress, there's a sort of a roadmap that makes sense, and you're able to sort of build this internal mind map of how everything is related to each other. But with this, since all of the methods that we deal with were developed independently, so sort of finding how each of those go together it's kind of like doing visual slam, I guess. You have to locate yourself within that global map of methods while also understanding each of them individually. So
Yeah.
hmm, that's definitely a class you want to take when you have a full semester. That's also a very rigorous class from what I hear. The professor who teaches that, she used to be my classmate when I was getting my master's here. She used to ace every exam. Oh, another thing. So I posted on Piazza about this, the sign-in sheet. I'm gonna put this away at 10:45 because um, I don't necessarily have a problem with people coming in late, but if you're just coming in last like 5-10 minutes simply to sign your name, then you're doing a disservice to yourself. You might as well just skip, and um, it saves people a trip to class. We're all adults here, so like I've skipped class a whole bunch too. So I get that some days you just don't feel like it. But just in the interest of being fair to everyone. All right, let's get into it. So to sort of help cement some of the things that we did last class, I tried to whip up a few examples and visualizations. I know a lot of it is pretty abstract when I talk about it in terms of equations or just like scatter plots that don't have that are just like dots on a 2D plane. Those don't really make much sense, right? So we looked at the k-means example earlier, and the way I'd explained it back then was we're grouping them by color, right? So to be able to group them by color, we also need to sort of plot them by color. So here, this is the sort of latent space within which we would be looking for our centers. And it's the space that is represented by red versus green, the respective intensities. So if you have both of those together, then what does red and green give? I should know this. Should be, what is it, yellow, purple? Either way. So over here we have colors that correspond to red, green, and whatever the blue part is. We were not taking that into consideration for this particular visualization, but we randomly initialize just any two of these points as our centers, and then look at the distances to every other point, and assign, oh, I didn't have the pointer on, my bad. So if I can, I don't think I can pause that, but starting out, both of those are kind of here, right? So even these points over here would be assigned to the pixel, the center that should be for the pink one. So once you look up what the value of that center is at the initial iteration, the color value that it returns will be green, and that's a wrong classification. So we iterate on it until we're able to get as few misclassifications as possible, and keeping track of the centers across iterations, we're able to see that it finds what a good center would be just by repeating that process. Another method or problem that we were trying to solve, you want to sign in now because I'm going to put away the sign-in sheet at 10:45. So what we were trying to do here, we didn't have any labels, and we wanted to do it, just see what we can do from the image itself. Just that's the only information we have. So we did an unsupervised approach, and we clustered it into two, which gave us a sort of approximation of what a segmented version of that image would look like. The other class of problems that we talked about that was supervised, and we looked at regression. So linear regression, the linear part has to do with the assumption that we're making about the distribution, which is that we would be able to find a line that approximates a trend in that distribution. So this is a data set that is baked into scikit-learn. It has a built-in function that lets you just download that data set. It's California house prices. And it's plotted, you can see the axis labels, right? These are readable. Okay, so we're comparing median income versus median house value. And the hypothesis is that there's some relation between the two, where if you know median income for a neighborhood, you would be able to sort of ballpark guess what the median house value would be. And there are just two variables there, so we find a relation between them. The way we do that is by setting the derivative of squared errors between the points to whatever candidate line you have. We set the gradient of that to 0 and solve. So that is a closed form solution, which we saw last class, can be represented as a linear system. And since it's closed form, that means we're always going to get a line, even if it doesn't necessarily describe your distribution very well. And the way we did it back then was just take for like one sample at a time. We learn how the line would fit to that, and then we take a new point and run it, just see where it falls when you plug it into our candidate line equation. So doing it one at a time generally isn't the case, like when you're looking at predictions that you're actually interested in. Ideally, it would be more than one, which is why here it's split into a training and test set. And the training set is what informs how the line is oriented and where it's at. And then we compare that with the test data to see if the error values are similar. And that gives some idea of how good a representation it is. We also talked about a different class of problem called classification, where in regression, we're predicting values outright. When we're doing classification, we resolve those values to something more meaningful and discrete, which is your class labels. We're able to get these by dividing our sampled space into regions, depending on however many levels you have to your tree, the number of decision boundaries that we end up with changes. And this is for the iris dataset, and we have 3 classes here. So using a decision tree, it's able to demarcate where each class would be. And we can make this more complex, adding more layers, using different features. The tree that decision boundary visualization was from. These are the set of features that it learned and how important it thinks each of those are, how many samples contributed to that particular leaf. And we have 3-level deep tree. And this is a representation of the labels versus what was predicted and how many of those we got right and which ones we didn't get right. And also an estimate of, this tells you what correlates with the actual class the most. So we can see that the length of a sepal is more closely correlated with whatever class is predicted than its width. So building on that, we dig a bit deeper into classification. So a typical sequence of operations when you're trying to classify samples in a space, you have whatever input variable going into whatever kind of classifier you're using. We saw trees so far, there's other kinds, and typically there'll be a weight and bias associated. So yeah, so that will spit out a set of values corresponding to however many outputs that classifier has, which is typically however many classes you have. So for a 2-class problem, you would have 2 values that the classifier spits out. And if we don't do anything with those values, up until that point, we're regressing values, right? But when we apply a threshold to it or do some sort of just put it through a function to do something with those values, then we can remap it to a different range, which allows us to do things like converting outright values to class labels. So in this context, what our classifier would do is give us what we want is the probability of a sample being classified as purple, given our sample, which is X, and we apply our weights to the classifier, sum them for all of the weights that we have, and all of the samples. And if required, we add a bias to change the y-intercept when we're dealing with lines. So let's work through a couple of examples just so it makes a bit more sense. So we have a binary classifier that means 2 classes. So we have 2 weights over here. It can either be purple or not purple. The weights correspond to the X and Y when we're training it, and we apply a threshold once it comes out of the classifier part. So any value, if it spits out a value higher than 0, then we'll say that it's purple. If it spits out a value lower than 0, we say it's not purple. We get a new sample, which is at 4, 5. We plug that into our weights matrix and multiply it, and that gives us a result of 1 in this case. So here, pretty straightforward. It's a value higher than 1, so the class that we predict is 1. It's a value higher than 0, so our final class is 1. If we added in a new point, oh, I should have had that one grayed out. It's this one here. This is at 3, 2, and we do the same thing, apply the same weights to it, and the value that our classifier gives for that is -1, and that's lower than 0. So once it goes through our threshold function, the label that we get is 0. And that gives us a decision boundary of X equals Y. So anything that's above that becomes purple. Anything that's lower is not purple. Now, if we shifted our entire sample space up by 2, we're adding 2 to our Y values uniformly, which you can see from the table over here. This is what we had earlier. Just added 2 to everything. Now, one way to do that would be the only thing changing here really is the y-intercept of the line. So we add a bias to our set of weights and keep the same threshold function and our new point. So this is our homogeneous coordinate representation. We have a 4, 7, and 1 because just so we're able to interact with the weights, and we apply our weights to it, and that gives us a 1, which is higher than our threshold of 0. So predicted label is 1, which is what we wanted. So the function that we were using to sort of post-process what we're getting out of our initial model It's kind of open-ended, and we could have values that go really high, really low. That doesn't really tell us much about what the input sample was, except what class our model thought it belonged to. Um, it doesn't give us any indication of how confident our model was that it belongs to that class, since it's just a naive threshold. So a better way that we could post-process what comes out of the model is apply a sigmoidal function, which this specific version is called the logistic function. And what it does is any value, any real value that you put in here, it will rescale to between 0 and 1. And that's useful because it tells us once the classifier spits out a value and goes through this, then we're on our way towards understanding the contribution of classness for each class to the final predicted label. So this gives us the probability that a sample belongs to either class. And the way we were thinking about our regression so far, we were using the closed form solution. And closed form, while the good part about it is that it guarantees you a solution, it's when you have a lot of samples, it's non-trivial to compute. So if we can optimize a surrogate function, a loss function, or an objective, or criterion, then that lets us estimate how good our representation is. So we need a function that we can use to choose what weights we use, that we can optimize. So something like our squared errors approach for fitting a line to a distribution where we're minimizing that. We can also maximize something else that describes it. A typical starting point for thinking about a function to optimize is the likelihood function, which lets us build the relationship between our weights versus the probability that our labels are correct. So we have the probability for a sample I that its label will be Y. And what we're given is our priors are the input variable X for that sample and the weights. And we sum this over all samples. Breaking it down, L is the likelihood function, W is the vector of weights. We already know that. We know X is the inputs. We know Y is our targets. And phi sub I is the product of all data points, the probability of observing our predicted label Y over the entire distribution. If when we're dealing with the positive class, applying the logistic function is straightforward. When we're dealing with the negative class, since we're using the logistic function, the good thing about it is it remaps our output space to between 0 and 1, and all our probabilities will sum to 1. So for the negative class, all you have to do is subtract the probability of the positive class from 1. And when we combine those, what we get is something that I think is kind of intuitive. So you have your positive class, its contribution, you have your negative class and its contribution and the product of those, and that gives us the likelihood of what weights we might see given our input and target. In practice, we don't use likelihood directly for the ease of computation, scaling, whatever reasons. We use the log likelihood, so just take the logarithm of both sides and propagating that throughout gives us this over here. Now this, while it is not closed form, so we can't do the thing with setting the derivative to 0 and solving for the slope and bias if we're dealing with a linear model, or just solving for the system of equations that would represent whatever model we're dealing with. But the thing that we can do is optimize it similar to how we minimize errors. Optimizing is basically an iterative process where we keep changing our values of weights until it either maximizes or minimizes some objective. We know that, but how do we actually optimize something? We need an algorithm that lets us govern the process of changing our weights and comparing it with whatever metric we're trying to maximize or minimize. Pretty universally, the first approach that someone trying to optimize something would be exposed to is gradient descent, where whatever loss function we have, loss function is the term is thrown around as a placeholder for any objective that's being optimized, but implicitly it's when you're minimizing something, and if not, then it's an objective or criterion. When you're trying to maximize it, it's just semantics, but they usually refer to the same thing. And we look at the how that is changing with each update in weights. Gradients have directions, and they point towards wherever slope is positive. So using that information, we can guide our optimization process to pick weights that lead you towards an optimum in your loss curve. So the loss function's derivative, wherever it has a trough or a peak, we try to seek that out. Just keep doing that until we get to a point where no matter which side you try to move, your loss is increasing. And once you get to that point, your model has converged and you found a good set of weights that optimizes your loss function. Formally, this is defined as a weight update rule, where you have your initial set of weights from which you subtract the derivatives of the loss function for a given set of weights, and how big the steps you take between each iteration. Those are that is encapsulated by the scalar eta that decides how large the steps will be. So if you have a learning rate that's really high, then you might see sample speed, your weights changing in a way that your predictions keep oscillating around the optimum and missing it. If it's too low, then in the case that you have more than one optimum, it might get stuck in that local optimum. Now, the weight updates can be informed. Ideally, they should be informed by everything that you're able to see as part of your training set, right? In practice, if you have 1 million samples, then making one change to every weight that you have and testing it on 1 million samples, um, comparing results of that one change, how it impacted all of those samples, uh, it, it's hard to do that for each and every change. So the assumption that we make is that a subset of the full set would still contain a similar trend to be modeled, and that subset would be representative of the larger distribution. So instead of doing it for the entire data set, every single update, we just pick a random subset, and J over there would be called their batch size. So instead of 1 million, I pick, say, 8 samples, 16 samples, and I do my number of update steps will become 1 million divided by 16. So instead of looking at one sample at a time for over the entire data set, we're looking at just 8 or 16 or 4, however many samples, and then we compare our model with what the ideal should be by looking at the error, and then keep doing that for the entire distribution. So that lets us make bigger updates because each update is informed by more samples than just one, and that lets us arrive at a solution faster. When we set the batch size to just 1, we're looking at each of them individually and going over the entire data set. We call that stochastic gradient descent because each individual sample is changing your model, and when it's more than one, but smaller than whatever the entire data set size is, we call that mini batch gradient descent or just batch gradient descent. So at this point, we have a classifier, or just we have a linear regression model. We have a logistic function that we're able to stick at the end of that to give us classes. We also have a function that we can optimize, which is our log likelihood function. And we have an optimizer now, which is gradient descent. So putting those 4 things together is equivalent of maximizing log likelihood, since to reframe this as log loss, quick aside, we'd just flip the sign on this. So instead of maximizing likelihood, you're minimizing loss. It's still the same update step, and we plug in the logistic regression approach in there. We're able to do that for 2 classes with the logistic function, since the way we formulated that was by assuming that they'll always sum to 1. So one class is positive, the other one is its complement. This works when we have 2 classes that we care about. If we have more than 2, that breaks down. So there's it's something that builds on the same principle, but extends it to work for multiple classes. And that's called the softmax function. So when your problem is no longer a binary classification, but a multi-class classification problem, you would use the softmax instead of sigmoid. And you still end up with a probability distribution that sums to 1. And you end up with classness, so to speak, for each class given a sample. The only things that have changed in here really are that we're also taking into account contribution for each individual class, which the Z vector will now contain however many raw scores as there are classes. And then once it goes through the function, we end up with our individual class probabilities. Linear regression that I had shown at the start was calculated with the closed form solution. So I couldn't really demonstrate any sort of optimization because the first solution that we got was optimal, that there was no change to be made over there. Did the exact same thing using gradient descent instead. We're still not classifying anything, but we're optimizing for as low distance as we can get to every point in the distribution. And this line is the one that minimizes that. And on the right, we can see what the error value is as it is optimized over multiple iterations. By the time we get to around 100, 150, it levels out. So that's as far as we're going to get with a straight line. Applying our regression technique to a classification problem, the only change that we talked about was putting in a logistic function, which gives you class labels instead of raw values, which the raw values, we usually call them logits. So our logits get remapped to class labels, and the decision boundary that it finds is what gets optimized. So again, it's a line separating two of them, but now we're spitting out class labels that converges around 20 iterations in. This is probably the hello world of doing machine learning for the image space. The MNIST dataset consists of a whole bunch of handwritten digits, and each of them is a 28 by 28 image. So when you separate all the rows and stack them behind each other as one single row, which is called flattening the vector, we end up with 784 pixels as a one-dimensional vector, and then we can apply 10-class softmax regression to that. And our model, well, for 10 classes, it's kind of hard to visualize a decision boundary. What I was able to visualize instead was feature responses, what our model thinks corresponds to a class 0, a class 1, 2, and maybe with some finagling with this, boosting contrast or whatever, we might be able to see something that resembles what we're looking for. Another thing to notice over here is that the regions that it seems to be prioritizing, that there's typically information closer to the center, so the farther away you get, it doesn't really care about those parts, and there's no features in this set of weights. So flattening this out would be 784 pixels for each class, and this is effectively how important each pixel is. So these are the weights for each class. Um, the bright regions it would emphasize, so for a 0, it seems to be somewhat more uniform than you would expect in a 1 or a 7. This simple approach, we end up with an accuracy of close to 95%. Over 95% is what Dr. Redmond had on his slides, so that's what I put in there. What I got was 91 something. Maybe if I'd let it run for a few more iterations, I would have gotten there. Beyond that, so adding a couple more ideas to our arsenal, we have support vector machines. These, I think, came about, these were popular in like the 80s and 90s, I believe. It builds on the idea of our linear classifiers. So if our sample space, in this particular case, there's a whole bunch of lines that we can draw that would split these two pretty neatly, right? Reason for that being that they're spread apart far enough on their own. If we are able to split them in different ways, then how do we find the one that's best? We go back to our same approach of thinking in terms of errors or distances and optimizing something over there. The way we do that is for a candidate linear model that splits your sampled space neatly. We also add two support vectors, and these are separated by a certain distance. So the goal is to find the line that has the support vectors with the maximum margin between them. So if I went back to this case, the blue line that's vertical, and tried finding the lines that intersect with our samples of each class, then it would be a very, very narrow margin. And once we change our slope, that increases, and then once we start getting horizontal again, that decreases. So there's a trend over there in terms of the width we get between the support vectors. So when you have a trend like that, we're able to take the derivative and find an optimum for that. So the assumption is that the points are linearly separable, which means we can draw a line between them that partitions the sample space well. We minimize the L2 norm of the weight and ensure that all the points are correctly classified with a margin of at least 1. So that's how far away these support vectors would be from our actual linear classifier. Points, this is always the case with whatever model we talk about. We talk about it in a vacuum initially, dealing with an ideal distribution that can be partitioned neatly, but real data is noisy, so we take that into account. We add a slack variable, which is how much of misclassification is acceptable to us, basically. And those cases, the SVM would be called a soft margin SVM. Person detection, Before I talk about that, everything so far, I know it's hard to keep them separate. I've tried to structure them sequentially in a way that they're kind of like building blocks that we all reuse them, but it is going to take a while to just cluster all of these ideas together in our heads. It took me a bunch of years. Might not be the case for you, but regardless, if there's anything that anyone would like me to revisit before I go into the person detection part, I can do that. Okay. Now we talked about a bunch of abstract math stuff. I showed you a bunch of visualizations, but in practice, what we care about is how we can apply these things to solve problems, right? So detecting people in images, regardless of what problem we're trying to solve, typically you would start off by, you need something to put into the model. So with these approaches, if it's an image, what do you put in the model? You can, you could put every pixel as it is in there and let the model try to figure something out based on color, luminosity, whatever, but that isn't really telling much about structure. So we want features that describe the structure of what's in the image to a degree. We have done feature extraction. Hog isn't one of the ones that we covered, but it's histogram of oriented gradients. So similar to how the image in when we were doing the Haar cascade face detection visualization, we broke it down into a bunch of blocks where we were looking for those Haar features. We do something similar over here and look at the general orientation of gradients within that region. And depending on what scale we do that at, and once we do non-maximum suppression or normalize it somehow, it starts to resemble what a person looks like. So this might correlate better than just raw pixel values, because this is color agnostic. It's also brightness agnostic. If this guy was wearing a pink shirt, it probably still would have looked very similar to what we have over here. So that's good. We can use that. We take these features, throw it into an SVM at every location and see what kind of responses we get. If we get a high response, then we could assume that there's a person there. The challenge with that representation was that it was at one scale. There was a method proposed in 2005 by Dalal and Triggs, where they trained SVM on Hog features for two classes, person, not person. And to deal with the scale and location challenge, they just run it at many scales and at every location. So apply the feature map, get responses, and put it into the SVM until eventually you end up with a positive prediction. So this takes over 10,000 evaluations per image. Not the best way to do it. How could we simplify this? So far, the sort of rationale that we've taken into things like the Gaussian pyramid were more algorithmic, but we can also draw inspiration from just the physics of things. So if you have a person, odds are that their head's going to be above their shoulders. Shoulders are probably going to lead to two arms. So the relative positions, if you break our model of a person down, these should usually be in the same place relative to each other. So we can deform our model to look for individual parts, because if you find any one of those, then you can look in that neighborhood for the other parts. Sometimes they might move, but it's still a useful approach to simplify the problem. So in practice, how this would look is we calculate hog features at a bunch of scales. Cases over here, we have the normal resolution, and we double the resolution and do the same thing, keeping our hog feature window size the same so that we get higher resolution feature map. And then we run the base model on the lower resolution feature map, which gives us an approximation of where we could potentially find people. And then at those locations where we have high responses in the original resolution feature map, we run our model on the, we run our parts models on the high resolution one. So since it's a high resolution feature map and we have a bunch of models, we only want to do this where we already suspect we'll find what we're looking for. And by doing that, that lets us be more confident about what predictions we're making by breaking it down into 2 stages like that. And then when we combine those and weight them based on location relative to the base model, that gives us our final prediction. Now, for parts, we can't define those directly because of people. You might have a picture of someone on a stroll or someone waving to someone, feeding a duck maybe. So the positions of their arms will be different from if they're standing in queue somewhere. We can use another SVM to predict where the parts might be. So we use a latent SVM to learn the positional relationship between parts. And by doing that, we're able to combine both learning relative positions and also actually recognizing each part. The final challenge to solve is that during training, we end up with a lot more negative than positive classes. So we emphasize only the negatives that are hard to classify. So this is called hard negative mining. We find regions within the image that are misclassified as people and use those as hard negatives when it is the background and we're predicting that as a person, that is easier to correct, so we don't fixate on that as much. Over here, we've gotten to a point now where we're extracting features. We have a model that is able to identify a general neighborhood of where a person is. Further refine that by looking at parts relative to each other. We're also learning the relationship between parts. That there's only one thing here that we had to come up with ourselves. it's time to throw words out. What is the one thing that we had to figure out ourselves to give the model? What is our model getting? It's not the raw image. It's our hog feature maps. So that's a choice that we made since we think that that will increase the likelihood of our model learning to identify a person because it has structural information. So an even better solution would be if we could get our model to figure out what it needs. So that we would do using, once we get to neural networks, where we learn what filters to apply rather than supplying it features that we extract ourselves. Sure, we could extract features ourselves, but it's nicer to be able to at least do a preliminary exploration and let a model find out how to represent the input on its own. So neural networks is something that I'll be starting next week. Just to give time for some of this stuff to sink in, because once we get there, I'm going to focus on CNNs, and there's going to be less of math and more of how information flows through a network and what representations mean at each step. Now, beyond that, I have a whole bunch of code that I wrote up for to generate all of those visualizations. I would like to just briefly skim through some of those. And I haven't decided yet whether I'm gonna upload these. I'm leaning towards uploading these because I don't think this would help with solving the panorama problem necessarily. And just being able to see how things are actually taking place, I think that gives useful context. So the first example that I'd shown was the k-means one. We start by loading the data set, which, oh wait, no, this is for an image. I'm sorry. So we load our flower image initially, convert it to RGB because of OpenCV image loading. Then this is typecasting, just rearranging the order, and then we choose how many clusters we want, and then there's built-in k-means that we're able to use, which is a part of where is that imported. Yeah, okay. So iterative process. We initialize centers randomly to begin with. We're choosing from all of the pixels that we have. So pixels.shape would return the dimensions of our image, and then we randomly choose 2 because the value of k over here gets passed in. Choose 2 pixels, and then assign clusters to them by looking at the distances, which is the L2 norm from our candidate centers that we initialized. Use that to assign them centers, and then those centers pixel values become the labels. then we compare that with whether that is actually the right label or not. And we keep repeating this until that happens. That's k-means. For the tree one, this I just directly imported a decision tree from scikit-learn, applied that. The iris dataset, we loaded that. We have our inputs, our targets, and that gets supplied to a model, and then we call fit, which optimizes our tree classifier. Then I think, yeah, this is probably the most useful one. So in here, I'm doing regression with the closed form solution by solving for the system when the derivatives are set to 0. And that is contrasted by this one where we're using an optimizer to find the best set of weights. A lot of my code is plotting, so you could the things that have a lot of figure kind of stuff you can ignore. But yeah, I'll upload all of these and feel free to play with them, change values, maybe change the data set, whatever. Doing is the best way to learn. So play with them. Yeah, the step size that I mentioned in the gradient descent plot is called learning rate in here. You can maybe start out trying to run it just for a few iterations to see if it works, because for 1,000, this took about, I think, 3 minutes on my computer, which it's really not a lot in the machine learning world, but it's just less rewarding when you're able to see that happen infrequently. So yeah, I'll share all of these. And what else? Whoever's teaming up, I hope you filled out the Google form. Then project proposals are due Saturday night. I'll be grading the first homework over the weekend, and I'll also give out the next homework sometime either Saturday or Sunday, depending on when I give it out. I'll give you a week from then. Yeah, that's it for now. I will see you all next week. Oh yeah, I changed that. Yeah, thank you. Oh, also, it's not mandatory or required thing, but I posted another Google Forms link about feedback. So that doesn't like change. It doesn't affect me directly, but if you put in like long form pointers on what you want me to do different, it's anonymous. So it'll help me serve you better. I'd appreciate any inputs, because this is my first time doing this, so any inputs would help. Yeah. Yeah. What's up? What time did you get here? I put the sheet in at 10:46. I had an alarm set.
Are we supposed to have 10 minutes of pre-trained model?
Hey, you can use pre-trained models as long as that doesn't directly solve whatever problem you're proposing in your proposal. So if you're saying you want to do object detection and you just pull YOLO and load pre-trained weights and run it, that's not enough.
So we can use architecture, but I mean, if we are not using the pre-trained weights and all, then what is the use of using that particular architecture? Why not build design from the scratch? If you are planning to use YOLO, then
I mean,
we
you
have
can
to use
still
weights.
use YOLO with pre-trained weights as long as you're maybe fine-tuning just the classifier part on something else, or your object detection is step one of a larger pipeline that does other things.
Like other things, as in like we have after the training we are developing some kind of application or something, some camera-based application using. So that will be.
So when you say application, when I'm saying as part of a larger application, I'm not talking about the way that I package it, but rather a larger use case that has multiple steps. So if you're thinking of object detection, since it's already so accessible, then I would like to see something like you're using object detection to identify a region of interest, and then maybe you're reconstructing 3D structure of the object that you detected somehow, something like that. Just combine functionality so that yeah, that I'm just trying to give you an example of my mindset. Yeah, because I mean, I don't expect you to train models like Clip or whatever, because yeah, computational resources are limited. I've mentioned what the deal with CCR is. It's kind of hard to get used to using it, and there's usually also a wait for when you can get a GPU. There's Colab's free tier, which lets you use TPUs and GPUs to train models, but that's also limited and it times out, I think, at 10, 12 hours or something. So in that sort of a setting, if you're freezing your initial feature extraction weights and then only fine tuning your classifier, that's far fewer parameters that you have to train for, which is in turn faster to train. Yeah, that's the.
But to get them proper accuracy, we need to like select pre-trained models which are available outside, both are like the professional ones. So if you fine tune any of the parameters or any of the layers there, then we have to train the whole thing with all the data sets. It will take time.
So the motivation behind me bringing up fine tuning would be, it wouldn't be to beat a benchmark, but rather because your sample space is different from what the model was trained on. So let's say you take a regular YOLO that was trained on normal RGB images and you want to adapt that to work with depth maps. So depth maps look different from your normal pictures, right? And in that case, you might see an improvement in performance if you fine tune for that representation, because even though the pre-trained weights might work on that, it's still outside of the original distribution that it was trained on. So in that case, you would find in just one example, or you could do thermal or something instead of that. If you have LiDAR data, you could flatten that to 2D, do something with that. Does that help understand the objective? Yeah, I don't want to. Yeah, I don't care if you're able to beat the state of the art or not, as long as you're able to solve a problem that you understand from start to end how you solved. Yeah, I'll update that. Someone told me that. Yeah, Saturday midnight.
In the office hours. So
Mhm.
have found an assessment of our perspective images with cancer targeting.
Mm.
So if we apply CNN or something on that, good enough for
Yeah, does that feel challenging to you?
and explain the comparative study of other
Uh, hyperspectral, what data set did you say it is?
diseases of cancer.
Okay. Hmm. Yeah. Where did you find the data set? Okay. So you're gonna have to include where you find the data set, because if you found it on Kaggle, then I'm gonna check whatever other Kaggle notebooks are there with that data set. Yeah, and ideally you want to go into it without even looking at those, so that like your approach is unbiased. And sure, you can compare with those notebooks later once you have your model implemented, and that will that could be a comparison part, or like what we could improve if some aspect works better. Yeah, but unlike literature review, normally you would do literature review before going into the project. So Kaggle notebooks are off limits. If you want to read papers that are similar to it, definitely would recommend doing that. So hyperspectral and CNNs. It, in terms of sequence of operations, what you're extracting from it, what you're learning, there's really just one model that you have to build. Would you say that that's challenging for you, especially considering there's two people working on it? That there should be a degree of uncertainty whether you're going to be able to do it or not. If you're 100% sure that, okay, yeah, this is easy piece of cake, I'll do it.
To figure that out, but the data set is okay, right? Like how you use that?
Data set isn't where I would start. I'd think of a use case, and think of how to implement a solution for that use case. But there's nothing wrong with that data set. The other thing that I was going to bring up to you yesterday, which I forgot to tell you, was there's a new style of network called CAN. These are really new, and these have a potential. These haven't been explored much. They're called Kolmogorov-Arnold networks. And what these do is, So a normal neural network, multi-layer perceptron, the activation functions that those use are um, fixed. So you have a tanh or a rectified linear unit, whatever. So the way they're doing it here is that the activation function is also learned. So that makes it a lot more flexible. And you're able to get away with far fewer parameters, connections, and less depth. Uh, you could try to think of a case where something like this would help. Um, so complex distributions that can't be modeled even with the kind of nonlinearity that we introduce with these activation functions, those are cases where this would shine. Now, what those cases are, I can't say off the top of my head. There's probably some potential uses that they've talked about in here or cases where this would work well. You could try swapping out an existing multi-layer perceptron classifier block from whatever pre-trained model you use with this and see how that helps visualize feature importance. Just throwing ideas out. Okay.
Like I'm having problem now getting a grasp of how big I should be. I'm not sure if I can do it alone or if it would require more skill master.
Uh,
Like I just want some help or if you suggest something. So I could do individually. It's just the idea is that
so from your description in the proposal, I'm hoping that I also get an estimate of how challenging you think it is based on how much exposure you have to thinking about problems in terms of images and features and weights and whatever. Because if you're coming from, say, spending most of your time thinking about maybe databases or things like the REST APIs or full stack kind of stuff, then this is a bit of a different paradigm. Okay, so yeah, with NLP and deep learning type of computer vision, especially if you're talking about language models, um, and if you're familiar with attention and transformers, what those do, sort of, you're learning a distilled representation of your of any input, right? You have a token, and it goes through a transformer which spits out an embedding. That embedding is projecting your token to a higher dimensional space that lets you separate it along a bunch of axes. So those principles are transferable over here also. So instead of embeddings for tokens, you have embeddings for patches of images, and those become features. Like you can think of those as whichever axes those would project to in that higher dimensional space are your feature axes, basically. So in terms of reasoning about what the model is learning and stuff, I think that you wouldn't have much of a challenge. It's just expanding that understanding to images. What did you have in mind for a project?
initially looking at visual prompting, but then I think that may be too complicated.
Mm.
For me to attempt.
Visual prompting. Oh, so like image generation from a prompt, or
You have images.
uh,
And there's one model called SAM. What it does is you mark like segments on the image.
okay.
can give it like 1 or 2 segments, or you can even give it a text prompt, and based on that, it creates.
Oh, okay, you're talking about segment anything?
a segment.
Okay. Hmm.
There was another one which gave like 2 images, one input, one output,
Hmm.
and then it gave another input. And the model has to create the output based on the initial input.
Okay. I think one way that I can sort of tell you what I'm not looking for is I don't want you to think about coming up with new model architectures, because there's smarter people than us who built these models, and conceptualizing what would make for a good part in a network is beyond the scope of this, and we don't really care about that. We care about um, extracting meaning and describing the visual world. So that having overlap with deep learning based stuff is a byproduct of just the times that we live in. Um, you don't necessarily have to dig too deep into all of that, as long as there's a problem that's being solved using what you can see. So
Everything in the prompt.
mhm.
That
uh, generating image from text, I mean, the like, what part of that would you be investing your effort into? Because to generate images from text, right now the way it's done is we have joined uh, text and image foundation models that learn a joint embedding space between image features and um, the likelihood of words showing up before and after each other. And when you have that joint space, then the idea is that if you encode text into the same embedding space and decode that into the image space, then you get a visual representation of that same embedding. There you would use something like Clip, which is OpenAI's what they use for DALI. Uh, so there's not much for you to do there, right? If you could think of maybe, okay, how about this? So you have videos of maybe uh, traffic signal intersections or something like that. You can try to detect if someone is jumping the signal, breaking it. So then you would have to, that's a composition of a few problems that you have to solve. So you have to identify whether the signal in the frame is red or not, whether there's a car stopped there or not, and whether it is, but you need to be able to identify when it starts moving and whether the light was still red at that point. So there's two things you're keeping track of: the state of the signal, which is red, yellow, green, and the other thing is the speed of the vehicle. So that's object tracking that you're doing. And then combining those, you're able to say something meaningful about whether it's jumping the signal or not. Would something like that, you don't even really need anything deep learning to implement a baseline of that. Do you want me to give you an overview of how a non-deep learning solution for that would work. Uh, markers. I don't see any markers here. Maybe I'll do it on pen and paper. So things that we know how to do based on class right now, whatever we've covered. If you have a frame, let's consider that a car. I'm not great at drawing stuff, just bear with me. That over there is a signal. You have both of these things in the frame. So first step would be, you could probably use something like YOLO or whatever to detect this. So you know where the signal is, you know where the car is. Then to keep, there's two problems that we want to solve. There's track the car, which is very basic visual odometry. You don't even need to go very deep into that. As long as you're able to just detect this in one frame. And here you can either classify this using, like you train a classifier to identify if it's red or yellow or green, or just divide the region of interest. So you know what your bounding box coordinates are because YOLO detected it. You can just divide into 3 and look at the dominant color in this region after converting it to HSV. So that way you don't need to train a classifier to do that. To keep track of this, you can just see how much each frame is, each bounding box is moving relative to the previous frame. So you'd have to do that in a loop, basically. Look at every frame in the video, see where the bounding box for class car is, and sort of plot its trajectory. You could also look for a line, because they're supposed to stop at a line, right, for the signal. And you can find lines using the Hopf transform. That's another way to solve it. So you understand what I'm trying to encourage is engaging with the problem and thinking about all of the ways that you can solve it. And I don't care about the how shiny the solution that you're using is, as long as you're enjoying the puzzle solving aspect of it.
Said decide on something is gonna mail you to ask if this is fine.
Yeah. Post on Piazza instead. Yeah. Send me a question. So this, if it feels too challenging, you don't have to go with that. I'm just trying to, the point behind me giving as many examples as I can think of is to get across how I want you to think about the project, what I want you guys to get out of it. Yeah, you're welcome.
So project using planogram company.
Using what?
Using OpenCV, object detection and then image classification for planogram compilers.
Planogram, what is it? I don't know what that is. Planogram compliance, okay.
What exactly is and where you have to use that.
Interesting. Is there No, I don't want a dashboard. That it's only going to eat into your time, and mm, I don't care about how you present it.
But is this project okay and is it
Uh,
worth to people?
I don't know about how this problem is solved conventionally. What do you know about the solution?
I just know the overview of it. First, we use object detection to find particular objects,
Okay.
and then we say this item does not belong into the shell.
Okay.
Most property.
So we care about the distribution of classes in an image. It's a bit of object detection and outlier detection. That's okay. Uh, is there an actual? I'm guessing there's a library or something that targets this. I see an Azure example.
But we just want to use
Anagram compliance API. Okay, so if what they're doing is behind an API, then you don't know how they're doing it. Okay. Detection. This is enough for two people. How familiar are you with
Not,
image stuff? I mean, I have no way of finding out if you are.
we are very familiar with machine learning models, deep learning models.
Okay. What sort of?
CNN
Yes.
models.
Okay. Yeah, it's a good starting point. I might ask you to add something if you, I don't know, just depending on your progress reports. Yeah, you can go ahead with that.
It's worth to be working on it.
Yeah, I mean, for now, I think that's fine and start. And I might ask you to add something that's maybe like adds 20-30% more effort. Yeah.
And in the project proposal, because we have not yet decided what models to use, should we mention what models we should be using?
The specific model, not very important, but the like the smallest functional problem that you're solving would be something like object detection in this case, right? So the sequence of those functional steps and how it ties together, what data set, and any candidate approaches that you can think of. Because even with this car at a red light example, there's a whole bunch of ways you can solve that, right? So I would like to see just from first principles how you would reason about the problem, just as a person trying to look at it and maybe write it down. And then what approach you take is secondary to that. You get the rationale, right? It's fine. Don't sweat too much about the initial proposal. This is a collaborative process. I want you all to have fun with whatever project you pick, and yeah.
So if it's okay if it's not a research idea, it's just
Yeah, it doesn't have to be publishable. That's not a requirement, because that's something that I would ask if you were, yeah. For this, the goal is that when you assuming most of you are going to apply for jobs, and I want you to have credible answers when someone asks you if you're applying for a computer vision or image processing type of role. You need to be able to think about the world in terms of features and representations and what you do with them. That's all it is.
Who will decide what models we are actually using? Sorry, please.
Okay, yeah.
Is it okay if it doesn't work and then we reach a point?
Um, don't account for that going into it. And start simple. So come up with a very rudimentary solution. So if you do something like so for this image here, one way I could do it is just by clustering based on colors. So the one challenge there would be that you have to know how many centers to pick, but you'd still be able to find like regions that are that have center labels assigned to them, right? So then if you find a block that has a different center label that's surrounded by other labels, it's just bunch of if-else conditions once you have that map, right? So that's your baseline then. That's the simplest solution that you can come up with. And then after that, since you are breaking down your problem into little functional blocks, you can choose which of those blocks is holding you back right now and find something that does that part better. And then when you put all of those together, you have a much better solution than you started out with. So this, just with whatever basic logic that you can come up with on your own without looking at any papers, you will be able to figure something out, right? So even if you have that at the end of the project, that's still a win. But ideally, it should be something a bit more complicated than just clustering that, because nobody does that in the industry anymore. Yeah. That is
Yes.
okay.
Thank you.
Yeah, you're welcome. All right. Who wants to go next?
Last class we can discuss.
Yes.
Instead of image clustering, we have to do image segmenting.
Okay.
Not apply it on underwater images or aerial.
Oh, right. Yeah, you guys. You emailed me or posted on Piazza, right? Because I heard underwater and I was like, wait, I know someone who's doing that. Uh, yeah, but it was your post that I was thinking of. Yeah. Segmenting for underwater, and what was the other one? Drones. What would you do with that segmented output? Like, why do you care?
Actually, I thought of doing aerial images for wildlife.
Okay.
Like the segment wildlife.
Hmm.
Higher some stuff.
Okay, that's fair. What else?
But there are a lot of implementations. Underwater, there aren't a lot of problems.
Hmm.
Sending
Underwater, what information do you have there? Just segmenting underwater. Okay. Well, one thing that I could think of, one use case, you could, have you done any like simulation or anything? So I was thinking underwater now, the coral reef the big one, what is it, the Great Barrier Reef, I think. That's been a subject of some concern regarding like global warming, all of that. It's getting smaller. So if you're able to, let's say, go around the reef in a circle while looking at it the entire time and segmenting throughout, then you can estimate the volume of the reef, and then this can be done multiple times over years to keep track of how that's changing. So something like that, maybe count how many fish are in a school of fish uh, when there's a whole bunch, or if a shark swims through it, how many there were before and after, so you know how many it ate. Something that tells a story basically, in addition to just whatever you're doing functionally, is ideal. So for fires, that's reasonable, but again, it's a single step, and I want a composition of steps, a sequence of steps that tells you something about what you're looking at. Maybe estimate, like bucket the fire into severity, probably. Or you can try to identify whether a fire is a wildfire or like an intentional fire, because they do that to like clear the forest also, right? Or like old weeds or whatever. So in those cases, I think the way they do it is they'll mow or clear a line, um, so that the fire has no fuel to travel across. So that is something that you can identify visually, um, a bunch of ways. What do you think? Yeah, I mean, you're free to do it as long as you can um, tell a story based on it that justifies why that approach is useful. So, doing, trying to identify whether it's intentionally set or whether it's natural, would be harder to do if you're relying on thermal images, because on thermal, that distinct line won't show up until the fire actually gets there, right? But when you're looking at it in normal visual light spectrum, visible light, like you'll be able to identify that part. So that is a case in favor of using normal visible light spectrum imaging to uh, and applying that to wildfires. Because otherwise, if all I care about is just um, monitoring when a wildfire shows up, I would use thermal on a drone. I wouldn't use visible. I'm not trying to shoot your idea down. Just uh, motivating the problem is also important. That's all. Yeah, if you have access to data from both that are matched to each other, then you can think of a case where having both would help versus having just one, and then quantify that improvement. Like, I'm not asking too much, am I? Underwater, I don't know. There was that fish population thing that I told you, like that there's this whole school of small fish swimming and predators go through, and then by what percentage that school shrank. Uh, if it's an endangered species, then that's probably something that those people would care about, the people who monitor that species. I don't know. Be creative with it and have fun with it. That's the important part.
For
Uh,
example, we'll have a moving curve and then a pedestrian crossing the curve.
okay.
So we'll be able to calculate the speed of the pedestrian and then the
Uh-huh.
speed of the car. Sometimes what happens is even if the signal is green for the car, the pedestrian starts walking. They don't consider the car is coming into their way.
Mm.
So in that way, if we calculate the distance of that walk and then the distance from the car to that car, we can see whether both didn't see each other or whether they will crash into an accident or not.
Wait. I missed a couple of. How do you quantify if they've seen each other or not?
They don't see each other. For example, cracks have happened only if both didn't see each other, don't see each other.
Hmm.
For example, the pedestrian is just putting a earphone and
Where are your cameras in this case?
we have some videos like that. Passing them by.
Yeah, I mean, I'm just wondering from whose perspective this is. Is this like a dash cam inside a car or a CCTV or no? Okay. Is there a class here now? Oh, okay. Yeah. Uh, hmm. Did you already have this idea before you came into class, or is this something just came up? Okay. Do you have a data set or something identified?
That's why man.
I mean, the idea can be applied, but see, there's a couple of challenges with the problem formulation. One is that CCTV cameras that you have are just single cameras, so there's no depth information. So a person, um, there's the problem of what's called scale ambiguity. Uh, when you only have 2D information, something can be really small and close to the camera and really large and far from the camera, and they'll still look the same size. And um, you need to have that information at least to some degree to be able to estimate position and things that are derived from position like speed or acceleration, whatever. Um, that's one challenge. And since you have to know relative position of a car and a person, right, in that case, so that while you'd be able to do it for one viewpoint, uh, the way cameras are placed relative to the region that you care about, that will change a lot, right? So if you have a CCTV that's say 100 feet away from one signal, it could be like at the other signal, which is why in this case the first thing to do would be find a data set that you might be able to use for this problem. Data availability is a first question, whether what the data set looks like, how consistent the uh, field of view is across sources. I wouldn't recommend going down this unless you already have a data set for this. Hmm.
Taking some of the posters that who are spread and who are moving
while moving, like how the
Okay, I understand what you're saying. You get pose and then try to figure out whether they're moving or not and whether they should be moving or not when they're moving.
they're not having person,
Hmm.
it is something like found and just classify whether the person is a
How would you identify whether a person is intending to move when they haven't started moving, or is the idea that the like once they start moving, you catch it? Like what are you using to what are you basing your classification on of whether they're moving or not? Because it's a time problem, right?
They may stop after.
Yeah. I mean, I fidget a lot when I wait at a stop sign, so it's,
Step and take off.
yeah. Getting posts is not hard. It's a problem that has a lot of very good solutions to it. Think about it a bit more, see if you can build on that. Maybe, I don't know, you could probably apply it to like sports videos or something, extract uh, poses of players playing football to estimate the trajectory of the ball like right as they're about to kick it and see how that compares with uh, where the ball actually ends up going, maybe.
Find out what when for Saturday we have to bend. For future we just have to put a foot.
Yeah, that's an interesting case that I don't think it's not like viral anywhere. So
I mean, we just need some videos. Like the rest.
so okay, this goes into activity recognition territory. Videos. If you have a simple way of building a data set, assuming there is no data set for this, then yeah, this is definitely something very interesting and that I think you can solve. I don't know what the usage policy for videos on YouTube and stuff is, because the one thing that you need to know is, or two things that you need to know rather, is the point at which the ball and the bat connect, and the other thing is you need labels for each clip for what kind of shot it is, and a way to identify the ball meeting the bat and then taking some seconds of video before that leading up to the swing. So that if there is no data set, then it involves a lot of scraping videos, some logic to identify how the frame where the ball and the bat meet. So that's one vision problem, basically. You could also get that from the audio, maybe just look for a peak in the spectrum.
Based on image, like for example, just taking the frame of the second where the bat meets the ball.
Yeah.
So that is enough for the estimation.
I don't know. I don't know much about cricket like that. If you think that how they're standing in the moment the ball connects the bat is enough to predict what shot it is, then you can try that. Having a few frames leading up to that will definitely help inform that better, and you probably wouldn't even have to model that explicitly. You could use something like an LSTM that has a memory mechanism built into it, so it takes that whole sequence of frames rather than a frame, and the trajectory part it'll handle on its own, right? You wouldn't have to estimate stuff yourself. Yeah, but I think it's a very interesting problem. You should definitely look into it, see what you can find. Data is going to be your main roadblock for this, at least initially. Getting a simple solution shouldn't be hard, and then at some point I may ask you to add stuff to it. Yeah, so good idea. I like it. Yes.
Last subset, let's say, how we discuss the project proposal, right? Like image recognition, like food volume calculation.
Right.
You said like you can use depth estimation like in the volume. Regarding that, I found a data set like there are only 2D images. But for 2D images, I'm not sure how to find the depth. Like, whether I need to convert them.
There are pre-trained. So if you look at monocular depth estimation.
The video, like there are some, I saw some there, but those are kind of videos. Whether the vehicle is approaching one other vehicle, calculating the depth between the two vehicles. It's a video, but I need to find depth for the image, right?
Yeah, I mean, a video is a series of images, right? So the model is, the odds are it's not looking at the entire video at a time, because a video can be of arbitrary length and your model expects a certain fixed kind of input every time. So usually it will be doing inference on every single frame, and then there'll be some logic to sort of smooth the predictions between frames.
Is there any idea convert?
Monocular depth estimation is a very, very active, or at least it was a very active problem. Just look for, yeah. There's all these models that do it. There's all these data sets. So you can use any of these pre-trained ones. I think this indoor depth probably might be relevant to your problem. Let's see what kind of depth maps they're predicting. So, interesting. I wonder why they're doing it like that. Oh, clever. They're also estimating force jointly. So yeah, this, I mean, I'm not sure about this particular network, whether it has pre-trained weights or not. But there's definitely at least one model out there that has pre-trained weights. It's just this. Okay, that's them comparing it. Okay, so they expect you to train this. They're not sharing weights apart from that. Correct. So model zoo, model hub. Instance. For there's this for tracking things using optical flow, not related to what we were talking about just now, but this is also cool. And So they use this to predict activity, I think. Like I remember seeing some sample of someone playing basketball, and it was um, estimating like how much each part is moving. So that also might be something that you could use, because it looks like similar to a depth map, sort of, even though it's not meant for that. But yeah, there's got to be some model that shows up when you look for monocular depth estimation. Normal depth estimation doesn't constrain it to having just one camera 2D. So one of these is bound to have the weights also. You can look into that.
So it's possible, right? Like for a single image, we can calculate the depth, right?
Yeah.
For the single object.
Mhm.
Is it possible? It's possible, right?
Yeah, and then after that, so once you have depth, then the next is structure. We don't want structure from motion.
Like, my flow is
Maybe
first we
mesh.
need to I'm gonna identify the object present in that image, and
I'm gonna find it.
and for that particular object, I'm gonna find the depth, and based on the depth, I'm gonna calculate the volume,
Mm.
and then
You can calculate the
calculate
calculate.
Yeah, you can do that 3D. See, there's this thing that doesn't even require you to estimate depth. But then in that case, your sequence of operations gets cut down to just one thing, right? Where you're estimating what the mesh of the surface 3D of the volume would be, and then it's just calculating its volume. So that's too simple if you end up using something directly for it. Yeah, I guess if you so here, depending on what, let's pick a sample paper and see what they're doing. Multi-view, okay, this stereo is not what we need. 3D reconstruction.
So what you're
Oh.
doing is converting the 2D image to 3D and calculating volume will be simple.
Yeah. So these, the first one that I opened at least, that expects stereo inputs. So you won't be able to use that for your 2D. What you can do is, so a normal depth map is generated like this. You have two of those, and then you compare you find out the disparity, and that is your depth map when you're looking at it from two sources. So since you're able to estimate a disparity map using two sources, you basically have left, right equals disparity. So if you take your disparity to the other side, you can estimate one perspective using the other one and an estimated depth map. You get what I'm saying? So normally you have left, you have right, and you calculate disparity, and this gives you a depth map. So you think of it as function of left, right, which gives you depth. So instead of that, if you have one image and depth map, then you can predict the other one, right?
Yeah.
And then once you have this, then you could plug it into something that expects stereo input. So that is, we are solving two problems to get a coherent solution. And then after that, you do the volume calculation stuff.
But I need to get the depth map, right?
Yeah, so for that, you would use your monocular depth estimation on just this one. So you take the left and you get
Oh, okay,
the
okay.
depth map. Uh,
By using pre-trained models.
yeah,
Yeah, I'll get the depth map and the left image and depth map. I need to calculate the right image and left bait by getting
Using
LR
left
now and need to calculate depth by using stereo.
once you have LNR, then you can use a stereo, what is it, multi-view,
Multiple.
3D something.
Yeah, got it.
So
And take a picture of that if you want. And you don't have to lock yourself into that. Keep thinking about it. If you come up with something that's more fun, then you can do that also.
Basically, until now, we got only one idea.
Okay, yeah, that's
If
Oh,
we find something interesting,
perfectly-
we don't. Like we're gonna post it as a post for you.
yeah.
Saying whether it will be sensation for that particular idea.
Okay.
Thank you.
Yeah, you're welcome.
I just used to remove the plot at this one.
Yeah, that's fine.
But for the, I mean, for each step, I have just put the image there itself. The axis.
So commenting out that line of turning off the axis, the reason I asked for that change is because the output of scaling, you won't be able to tell if it's doing anything without
While
axis.
in it, I just put the image, so there it's it shows the axis.
Yeah, okay, that's fine. You're welcome. Mm.